Hi. So I've started section 1.4 and 1.5 and feel ready to start on the problems. In the meantime, the weather in Denmark has changed to November weather, despite we are still in the middle of October. So we have total cloud cover with low clouds, so it's dark and moist. Well, that's it. So let's go to the problem. So that's the first one. We have a lattice given by these two complex numbers and these two, and if they are the same and only if there will be a matrix with determinant plus minus 1, so that, yeah. Now that sounds eminently probable or likely. If this holds, then the opposite should be with A, the inverse to A, and the product of the determinants is unity. So, and they are integers, of course, the determinants, so plus minus 1 are the only possible ones. So we just have to show that this relation holds, which also sounds eminently likely. But it's the column vector with entries. Okay, so horizontally we have the two numbers. We just consider them to be 2D vectors instead of complex numbers, so that's the coordinates. And of course the complex number is F12. Oops. F11 plus I, F12. So these we call, the components are called F1 and F2, and here the same ones. All right, now the lattices are the same, which means that this vector lies in this lattice, so that omega 1 alpha beta are integers, and this means that omega 1, that was F1, F12, but we just write it like this, like the vector it is. And now we can write it as a matrix. It's annoying doing these details, but to make it totally clear, that's the only way to go about it. and it should be written as some matrix times the omegas I realize this is trivial, but it's work that has to be done nevertheless. So this must be alpha and this must be beta. Then the first row, that times that gives this, and that one times that one gives this. And then by analogy it must be the same etc. So that's it. And I think once we've done this work, then it's quite clear that gives us another point really, that every time we have an integer matrix, we get this way a point in the lattice. And since it's an integer matrix, the determinant is an integer. So all pair of lattice points have a span, a parallelogram, or whatever it's called in English, with whose area is a multiple of the parallelogram spanned by these two vectors. So, Now, what have we proven here? We have proven that if the lattices are equal, then there is a 2 times 2 matrix with determinant plus or minus 1, so that this holds. And the other way is trivial, isn't it? If this holds and A has determinant 1, then it has an inverse vector. So yeah, inverse matrix. Right. So I believe this solves problem 1.